Okay, I just want to let you know that these are the first full sentences I've even attempted to speak in the last 36 hours because my voice is messed up. It's like that chest cold kind of became laryngitis, and I feel okay, but I can't really talk. So you all know I can write almost as fast as I can talk. So there might be a lot of writing and not too much talking today. Okay? But it's an important class, and I didn't want to miss it. So, and for those of you watching at home, sorry about this. And we don't have an ASL interpreter to help us out here. But are there any questions about anything before we start? I still haven't figured out the mean on the midterm. I meant to do that, but I don't use that statistic for any reason, as you know. Right? Okay. All right, so I want to start talking about game theory. And I'm sort of going to give you a quick crash course in game theory before we move on to the evolutionary side of it and how it fits into this class. And there's a handout for this stuff that I hope, you know, it's been available since the beginning of the semester. It's the same one I used in 2012, so I didn't bother editing the date on it. But anyway, the whole idea of game theory is situations where agents are allowed to make choices to help themselves, but what happens to them depends not just on what they choose, but on what everyone else chooses. So how do you model that mathematically? So what is a finite game? A finite strategic form game. It's the animal we're going to be talking. By the way, who has had some game theory in another class before? Which economics, maybe? Yeah, 2850. Anybody else? Okay. A finite strategic form game consists of the following pieces. Okay, first of all, there's going to be a set of agents, n of them, and these are called players. And we denote them by player 1, player 2, up through player n. And by the way, even though the bulk of our discussion is going to be focused on two-person games and the way they play into evolutionary game theory, I'm going to give you all the definitions for things like, you know, strategies and Nash Equilibrium and all that stuff for n-player games because they're pretty easy to understand in that context. So you have a set of agents, n of them. They're called players, player 1 through player n. For each agent, I, so I is going to run from 1 to n, a finite set, capital A sub I. And what is this set going to be? This is going to be the set of actions that player I can take. These could be the same for all I. They could be different, but they're finite. Okay? And for each player I, let's keep using the word agent for now. Let me, oh wow, the good eraser from early in the semester. But I think this one's probably better. Softer. Yep. Okay. So for each agent, I, a payoff function. And what is this payoff function going to be? It's going to be a scalar valued function, u sub I, from the Cartesian product of all the action spaces into the reals. Is everyone familiar with this notation? A1 cross up through AN. Okay. It's the Cartesian product of a bunch of sets. It's a set of all ordered n tuples, where the first one comes from A1, the second one comes from A2, and so on. And the idea here is, let me just give you the background idea here. So recall the notation. I'm violating my rule by using recall in the middle of the lectures. A1 cross A2 cross AN is the set of all ordered n tuples. A1, A2, these are little letters up through A sub n, where AI comes from AI for all I. Okay? So that's what that notation means. And what is the idea here when it comes time to play the game, every player, and this is going to happen all at once, and we'll get more into the details of that a little later on, will take an action from his or her action space. So when it comes time to play the game, when game is played, each player takes some action from his or her, and remember last time talked a little bit about all the games people play with the genders and game theory. I'm not going to sweat about that. From its action space. Okay? And what results is an n-tuple of this form, which is called an action profile. In this set of all possible actions, crossed with each other. And another word for an action profile, in some sense, that people would use is an outcome of the game. So alternatively, an outcome of the game results. And in this sense, outcomes are in one-to-one correspondence with action profiles. And once the outcome results, each player collects his payoff as a function of the outcome. So if outcome A1 up through AN results, action profile, outcome whatever, player I receives payoff u sub I of that outcome or action profile. And I'm going to try to be consistent and put capital P for player because that's the way they do it in books and stuff. And I think that's the way they do it in the handout as well. Now, what are the background assumptions? So hovering in the background are two assumptions. And these are sort of multi-headed monster assumptions. Okay, the first assumption is about the players. Each player, or every player, is rational in the following sense. He's rational in the sense that he wishes to act so as to maximize his payoff when the game is played. Now the problem here is because the payoff to player I that comes from a given game outcome depends not just on what player I does, but what all the other players do, in general, there's going to be no way for player I to be sure that he's acting in such a way. Right? Is this funny or is it my voice, you guys?
We would never laugh.
It's about something else. You got funding for your thing? No. You don't know yet. Right. Okay. So you haven't answered my question. What's so fun? You don't have to tell me. Okay. All right. Each player is rational in the sense that he wishes to maximize the access, so as to maximize his payoff. We'll have more to say about that in a moment. And the second thing, and this is very subtle and deep. And I'm going to give you another handout on this that my ENGRI buddies have seen before. That includes Matt and Randy. Let's see, anybody else? Andrew, yeah. Okay. That everything here, the whole structure of the game, and what do I mean by the whole structure of the game? I mean the number of players and their identities, or whatever, the action spaces for each player, the payoff functions for all the players. All those things is what's called common knowledge among the players. What does that mean? It means that, technically, it's a list of infinitely many assertions. Every player knows it. It being the whole structure of the game. Every player knows that every player knows it. And you go on and on like this, and you get up to statement N, or statement K, say, because I've used N for the number of players. Statement K plus 1 is every player knows that statement K holds, and so on. Okay. So common knowledge is an infinity of statements about people knowing stuff. And you may think, oh, you know, what's so subtle about that? Well, I suggest you look at the handout. I'm not sure if it's visible right now, but it's up there somewhere. Joe Halpern in computer science is an expert on this kind of stuff. Okay. All right. Now, there is a nice sort of graphical, pictorial way of representing two-player games, especially small ones. So here's a convenient way to represent two-player games. That is to say, n equals 2. And that is what you do. You have a matrix. Action space for player 1 indexes the rows. Action space for player 2 indexes the columns. And entry KL is the payoff is of the form U1 of AKAL. And I don't know how to write this. Let's say entry A comma B, say, is of the form U1 of AB comma U2 of AB. This is easier to do with an example than in general. When A in A1 indexes row, and B in A2 indexes the column. So the point is, the locations in the matrix are in one-to-one correspondence with outcomes, and in that position in the matrix there appears the payoffs to the individual players according to that outcome. So the locations in the matrix are in one-to-one correspondence with outcomes, and the entries at a location, the entry at a location is equal to U1 of that outcome, comma, U2 of that outcome. Okay, easier to say, show in the context of examples than in general, so let's look at a couple. And they're going to be 4 two-player, 2-action per player games that we're going to carry along through this whole discussion as examples that will illustrate all the important points, and they're all classics. And then there's going to be 1 2-player, 3-action game. Can anyone guess what that's going to be? Say it right. Yes, it's going to be scissors, paper, rock. Okay. So, for example, this is the most famous game of all. The Prisoners. And there's a lot of debate in the field about where to put the apostrophe or if to put one at all. I insist on putting it after because I think of there being 2 prisoners. Dilemma. Okay. N equals 2. 2 players. A1 and A2, the action spaces are both equal to C comma D, whatever those mean. And here are the payoff functions. U1 of CC and U2 of CC are both 3. U1 of DC, U2 of CD is equal to 5. U1 of CD and U2 of DC are both 0. And U1 and U2 of DD are both equal to 1. And here's how you represent that in a matrix. The actions for player 1 index the rows, the actions for player 2 index the columns, and the entry in a given location is the pair of payoffs that accrues to the players given that that outcome occurs. Okay, this one you've seen. And you've seen a description of what this is supposed to represent. What is it supposed to represent? It's like one of those situations on Law and Order, especially the one with Vincent D'Onofrio, Criminal Intent, where they put the 2 suspects in separate interrogation rooms and they try to get them to rat each other out. Okay? And ratting out is defecting. That's what D stands for. And keeping quiet is cooperating. And if they both keep quiet, then the DA can't prove a strong case, so they only can throw them in jail for a couple days instead of many years. And so the players make off with these payoffs if they both keep quiet. If they both confess, if they both rat each other out, then they can throw the book at them, and so the payoffs are lower. And if, say, player 1 rats out and player 2 keeps mum, and player 2 really gets the book thrown at him, payoff of 0, and player 1 gets rewarded somehow with maybe a suspended sentence. Okay, so you've seen a description of that. Okay, another example. This is the second most famous 2-player game. Battle of the Sexes is what people call it. And I try to make it kind of gender-free in a way I'll tell you in a minute. Okay, so again, n equals 2, and the action spaces are the same. Again, and they consist of C and B. I'll tell you what those stand for in a minute. I'm not going to write down the U's. I'm just going to write down the matrix. And that'll describe the situation. It's supposed to arise here. So you have your action spaces indexing the rows and the columns, and up here you have 3, 2, 1, 1, 1, 1 down here, and then 2, 3. Okay. What is this supposed to represent? The classic description is the following. You have this couple, male and a female, right? And they're trying to decide what to do some night. And the choices are go to like a ball game, right? The classic version is, you know, go to see a prize fight, and that's what the man really wants to do more. And then the female really wants to go to the ballet more. So that's championship bout versus ballet. Okay, now, some authors turn it around. They try to be cute. They say, well, the woman wants to go to a fight, and the male wants to go to a ballet. Eye roll. Okay. So, you can also have it like two brothers, say. One of them wants to go to the club, the noisy techno dance club. The other wants to go to a swanky martini bar. So that's the way I usually phrase it. Okay. All right, so what does that mean? What is it supposed to be? Well, depends on my mood. Which one do you want to go to? Can you give a steady answer to that?
Go to the club.
Okay, fair enough. All right, so anyway, the idea here is that if they both go to the club, player 1 gets payoff 3 and player 2 gets payoff 2. If they both go to the bar, it's the other way around. But if one goes to the club and the other goes to the bar, they're both getting low payoffs. So the point is, they would rather do something together CC or BB than not, which would be the other ones. And player 1 prefers CC to BB, and player 2 the other way around. Okay, so that's the battle of the sexes or whatever. Okay. All right, so these are just examples of setting up these pictures and games and payoffs and everything. All right, now I haven't talked at all about, you know, how do they solve this problem of acting so as to maximize their payoffs and all that kind of thing. So let's talk about that. Okay, so back to the main discussion. When it comes time to play the game, every player is going to take an action. Okay? Kyle?
Why isn't the bottom left outcome lower than the top right? Because isn't that like the worst possible thing? Like, why don't you
It is. But this is the traditional way they do this game.
keep them equal?
Yeah. Yeah. It changes a little bit things, what's going on, but not that much.
What did he want to change?
He wanted this to be worse than this for both players. Because in this case, each of them is going out separately to the one he doesn't want to go to. Okay. Or I should have to say he or she if I want to keep it heterosexual, which is the classic way of doing this game, but there's no reason to do it that way. Okay. So back to the main discussion. Okay, so how do the games get played? Okay. Each player, remember, they all know what the game looks like, and they all know that they all know what the game looks like, and so on, ad infinitum. Prior to playing, each player ponders the game in isolation, without talking with any of the other players. They go off into a room by themselves and they stare at this game. And if they're like me, they're very cautious, and if they're like Max, they just, don't even really think about it. Okay. So prior to playing, each player ponders the game in isolation and comes up with a plan. Of action. What is a plan of action? There's a one-word name for that in game theory. It's called a strategy. Okay. What form do strategies take? There's two kinds. Two flavors of strategy. For a given player. Say I, player I. One of them is a pure strategy. What does that mean? They're all selfish, all the time. Everyone wants to do what benefits him the most.
But he doesn't care about what the other players want to do.
He doesn't care about what happens to the other players, but he has to care about what the other players are going to do.
That might affect him.
Exactly. But a pure strategy it's simpler than that. It's a plan to take a specific action in his action space. So a pure strategy, which is a plan to take one specific action in AI when it comes time to play the game. Okay? And a typical notation is going to be S sub I. S sub I is a pure strategy for player I. And S sub I takes the form, and I'm going to be really pedantic here about distinguishing between strategies and actions. This is something that a lot of game theory texts are a little bit sloppy about, but I think it pays to keep them separate in our head. Play, action, A sub I for some. A sub I and A sub I. That's what a pure strategy is like, a marching order of this kind. Okay? So, for example, the possible pure strategies in the prisoner's dilemma for each player are going to be play C or play D. The possible pure strategies for Battle of the Sexes for each player are going to be play C or play B. Okay? The other kind is called a mixed strategy. Okay? Now, what is a mixed strategy? A mixed strategy is going to be like a plan to proceed as follows. When it's time to play the game, I'm going to spin a spinner, a random spinner, whose wedges are allocated across my action space, and pick whatever action the needle falls in. So this is a plan to take an action chosen at random from capital A sub I according to some probability distribution. On A sub I. Okay? And a typical notation for that, and this is a very frequent thing that happens in game theory. If you have a pure something, it's a Roman letter. If you have a mixed something, it's a Greek letter. So guess what S becomes? Yes. Okay. So notation. Sigma sub I is a mixed strategy for player I. And I'm not going to write down a corresponding thing. It takes the form so and so. I'm going to look at these example games and show you the schematic we use for that. So a typical schematic representation for mixed strategies. So, for example, in the Battle of the Sexes, how about sigma 1 equals, say, 2/3 C plus 1/3 B. What does that mean? What does that schematic notation mean to us? This means, quote unquote, sigma 1 is a mixed strategy for player 1, dictating that he play, we have to use the subjunctive here, C with probability 2/3 and B with probability 1/3 when it's time to play. Okay. So the idea here is this is a plan to spin a spinner, 2/3 of which is allocated to C, 1/3 of which is allocated to B, and whichever wedge the thing falls in, that's the action you play. Okay, so prior to playing, each player ponders the game in isolation, comes up with a plan of action. A plan of action is either pure strategy or mixed strategy. Then he puts that plan of action in a sealed envelope. Okay, so having arrived at a plan, of this kind, either a pure or mixed strategy, each player, and this is the way I prefer to think of it. You don't have to think of it this way, but writes it down, sticks in an envelope, and hands the envelope to a referee, whatever. And the referee does all the spinning and playing of actions and all that kind of stuff. Plays out the strategies and doles out the payoffs. Okay, now when the strategies play out, each player will actually be taking some specific action in the game. But when they plan in trying to maximize their payoffs, they have to look at expected payoffs. We'll see that in a second. Okay. So anyone have a question about this so far? Yeah, Trevor.
So in this setup, there's no way for a player to change their strategy in response to observations?
Nope, not in this one-shot setup. Later, when we talk about repeated games a bit, you'll be able to plan your actions in subsequent stages based on outcomes of earlier stages. Robert.
So in
It's a one-shot. It's a one-shot. Okay. Yep.
When we're doing a pure strategy, could, in this case, like Battle of the Sexes, could player 1 choose B even though he doesn't like B?
Yes.
Okay.
Yeah, like for example, we'll get to this in a second, but if player 1 knows that player 2 is like hellaciously stubborn, will never ever want to do anything but B, has reason to believe that, then player 1 is going to want to choose B, right? See? Because player 1 gets 2 rather than 1. Right. Any other questions? All right, so let's look at these 2 example games and then look at one other. Maybe 2 others. Okay. So, in the prisoner dilemma. Okay, let's look at that one again. So we have 3, 3, 5, 0. Or I always write that down wrong. You have to do this every single time. Just watch that as I do that. Okay, I'm player 1. Okay. I have to go into a room all by myself and figure out how to play this game. Figure out what my strategy is going to be. Right? Okay, so I look at this and I say, okay, I have no clue what player 2's strategy is going to be. I have no clue. So what happens if when the game is played, player 2 ends up playing C, either as a result of having a pure strategy of play C or as a result of having a mixed strategy and flipping the coin, having a come up C, what's the better thing for me to do? Well, if you look at this, you say, well, if I play C, I get 3. If I play D, I get 5, right? So, if player 2 happens to play C when the game is played, I will want to play D. Okay. What if player 2 ends up playing D when the game gets played, either as a result of a pure strategy to play D or as a mixed strategy that happens to come up D? If I'm playing C, I get 0. If I'm playing D, at least I get 1. So what player 1 says, looking at this, is player 1 thinks, I don't know what player 2 will do. But if he plays C, I'm better off playing D. And if he plays D, I'm better off playing D. Thus, no-brainer, it's clear that my best strategy, and remember, best means maximizing my payoffs, is, quote, play D. In fact, that's a pure strategy. So that's what player 1 thinks. Player 2 thinks the same thing. Exactly. Except he replaces player 2 in the sentence with player 1. So player 2 thinks similarly. And strategizes play D, just as player 1 does. Then they come out of their little isolation booths and they hand their envelopes to the referee. The referee slices them open and finds that both of them want to play D. And so they both play D. He hands them $1 each or something. That, despite the fact that were they both to play C, they would both make off with $3. Matt?
Player 2 plays D, wouldn't you want to play C?
If player 2 plays D, player 1 is looking at 0 and 1.
I was looking at the wrong.
Yeah. It takes some practice to... Drew?
Is it common knowledge to players that their opponent is right?
Yes. Yeah, the whole everything about the game. Everything.
Player 1 should be able to deduce that player 2 is also going to come up with play D, right?
Mm-hmm.
So instead of player 1 thinking, I don't know what player 2 will do, player 1 would think, player 2 is definitely going to play D, but it's still my best option to play D.
Yeah. In this case, it doesn't matter. You don't have to go beyond each player knows the structure of the game level. In the handout, there's an example where you have to go beyond in order for player 1 to make a decision, he has to know that player 2 knows the structure of the game. Because then it will become obvious what player 2 is going to do, from which it's obvious what player 1 should do. But in this case, you only have to go one level into the common knowledge maelstrom, vortex, whatever you want to call it. Good question, though. Yeah, Robert.
Is there any case in which is there any level of thinking for these kinds of games in which they'll realize that bishop will play C?
There's no level of thinking when there's no communication and they're both rational players that will make that happen. And in fact, you can prove that we might end up doing this at any finite iteration of the prisoner's dilemma. The only possible outcome is going to be defect on every stage. In equilibrium. We haven't gotten equilibrium yet. But anyway. Other questions? Okay. Let's look at the battle of the sexes. See if we can pursue some similar kind of reasoning on that one. So here's the game. Okay, so I'll be player 1 again. So I'm the one who wants to go to the club. More than that. Okay. So I go into my room, I think about this game, I stare at it for a while, and I say, well, I don't know what player 2 is going to do, right? So what if he or she, whatever, what if he or she plays C when it comes time to play the game? Then certainly I'm better off playing C, right? I get 3 instead of 1. On the other hand, what if he or she comes to the game and plays B? Well, then I'm better off playing B, even though I don't really like B as much as C, because I get 2 instead of 1. And I don't know which one player 2 is going to do. And player 2 could even play a mixed strategy that could land on either C or B. So if I'm player 1, I don't see an obvious way to act. Okay. And I claim that there isn't an obvious way to act here. And there isn't an obvious way for player 2 to act either. So there's no sort of quote-unquote obvious, that's how little kids spell obvious strategy for either player. Okay? As there was in the prisoner's dilemma. Does anyone disagree with that? It's like a challenge question. So it's like I'm threatening to beat you down if you disagree. It's not meant to be that way. Okay. Hmm.
We're both thinking that same thing.
Because then you have like, I don't know, 0 or something. I don't know.
Like put zeros there? Then if that means if I'm player 1, I want to avoid B. If I'm player 2, I want to avoid C. So the outcome becomes CB, which is lousy still. Yeah, I mean, I don't think there's an obvious way. But yeah, good ideas. All right, now we haven't talked at all about, mixed strategies and stuff. Let's look at another game where mixed strategies are, in some sense, the only thing that makes sense to play. Okay, so before we do that, let me just mention so here's an aside. When players play mixed strategies, okay, so say for example, sigma I for each player I between 1 and n. I don't think I'm contagious anymore, by the way. Now this is all. You know how when you have a chest cold, you have that sort of mop-up phase where for like a week or two you're like coughing up little globules every 3.5 hours or so. No? You know that, right? Okay, well that mop-up phase never really, I kept coughing but no globules, and that's what made this laryngitis happen. Okay, so anyway, when players are playing mixed strategies, then we use the following, we use the notation U sub I of sigma 1, sigma 2 through sigma n to represent, and this is a slight abusive notation, the expected payoff to player I when the game is played. Okay. And the expectation is taken over all the little probability distributions on all the individual action spaces that the individual mixed strategies induce. So this is with respect to the probability distributions on A sub I, 1 less than or A sub j, 1 less than or equal to j less than or equal to n, that the sigma j less than or equal to j to n less than or equal to n induce. So if, for example, player 1 plays 2/3 C plus 1/3 B in the battle of the sexes, then player 2's expected payoff to playing C is going to be 2/3. Well, let's just do it. So, for example, if player 1 plays sigma 1 equals 2/3 C plus 1/3 B in battle of the sexes, then player 2's expected payoff to playing C is what? Can anyone tell me what it is? Say it louder. Okay. This is a good reality check. In this game, player 1 is going to flip a coin or spin a spinner when it comes time to play the game between C and B. With probability 2/3 it's going to come up C, with probability 1/3 it's going to come up B. If if I'm player 2, or if you're player 2, what's your expected payoff to playing C against that? Well, you're going to get 2 with probability 2/3, and you're going to get 1 with probability 1/3, right? So it's 2/3 times 1 plus 1/3 times, or 2/3 times 2 plus 1/3 times 1, which is 5/3. Right. This 2 here is just U2 of CC. This 1 here is U2 of BC. Got that? Okay. So anyway, so here's a game. This is another one of the classics. Where only mixed strategies seem to make sense. This is called matching pennies. And it goes like this. Here's the game matrix. And I'll tell you the scenario it's supposed to represent. By the way, this is a special kind of game. Because if you look at the payoffs for any outcome, what player 1 collects is equal to minus what player 2 collects, and vice versa. Anybody know what that kind of a game is called? Zero-sum game, exactly. And one of the classic, this is an example of one of those overuse of science kind of things. A thing that people frequently say, like at the level of popular culture news, is such and such and such and such is a non-zero sum game, but they don't really know what that means. Okay. It's really a non-zero sum game when you get right down to it. And the reporter nods astutely, you know, and whatnot. Now, I'm just being critical, but whatever. Michael.
So I was just wondering, player 2's expected payoff is directly based on the strategy of player 1.
Absolutely.
So can he know that at a time or no? Because the player 1 strategy could change. Isn't it the mixed strategy?
Player 2 has no clue what player 1's going to play. Player 2 can't plan his action or strategy, whatever, based on foreknowledge of what player 1 is going to do. That's what makes game theory hard. Okay. Anyway, all right, so what's the scenario this is supposed to describe? You've got 2 players, and you usually visualize them as little kids, right? And they each have infinite vats full of pennies. And they pull out a penny and they turn it up either heads, that's H, or tails, that's T. And if the 2 things that they turn up match, kid 1 gets both pennies. So that means he gains 1 penny and kid 2 loses 1 penny when they match. Other way around, the other kid 2 gets both pennies. So kid 1 loses, kid 2 wins. Kid 1 loses, kid 2 wins if they don't match. Okay? So that's the matching pennies game. Now if I'm kid 1, right? So this is 2 kids. Turn pennies face up simultaneously, either heads or tails. And kid 1 gets both coins if they match. And kid 2 gets both if They don't match. Okay, everybody understand the scenario? Okay, so I'm kid one. What do? I have this penny. I have to decide whether to turn up heads, turn up tails. If I turn up heads, the other kid turns up heads, I win. But I don't know that he's going to turn up heads. I have no reason to suspect, except, like, for example, when I was a little kid, coin flips, I always called tails. When is it call in the air, I'd always say tails. I don't know why. My brother would always say heads. So in that case, you might have a reason to believe that the other was going to do that, but I don't see how to play this, resolutely turning up a head or resolutely turning up a tail. So, like the battle of the sexes, there's no obvious way to play. No obvious strategy for either player. And unlike the battle of the sexes, I don't see how a pure strategy is ever going to make sense if there's any chance of the other player playing what you don't want them to play. Okay, so let's take the 3-minute break, and then we'll look at the mixed strategy idea for this game. Okay. Anyway, so let's look at some mixed strategies. And in particular, I want to look at, suppose each player plays strategy 1/2 H plus 1/2 T. And here I'm using schematic representation of a mixed strategy. Everybody get that? We're going to be using that a lot. Okay? So you can how can you implement this physically? Each player can just pull a penny out of his vat and just flip it in the air and have it land the way it does. And however they land, that's who determines who gets the pennies. So, for example, by flipping his penny and playing the face that's up. Okay? That's a good way to play 1/2 H plus 1/2 T. What are the payoffs to the players if both play those strategies? Let's go through it. I mean, this is pretty obvious. Like the payoff to each player, each outcome occurs with probability 1/4, right? 2 heads could come up, 2 tails could come up, so on. So thus, the expected payoff to player 1, or to each player, is going to be 1/4 times 1 plus 1/4 times minus 1 plus 1/4 times minus 1 plus 1/4 times 1 equals 0, because in 2 of the outcomes, each player gets 1 in 2 of the outcomes and minus 1 in the other 2 outcomes. Okay? And in fact, if you think about this for a second, if I'm player 1, kid 1, whatever, and I know that player 2 is planning to play (1/2 H plus 1/2 T), I can't do any better than to play that mixed strategy. But it turns out also, no matter what I play, I'm always going to have expected payoff 0. So it doesn't matter what I play. I could play H or T or some mixture, say alpha PT pH plus 1 minus PT. My expected payoff will still be 0 if player 2 is playing 1/2 H plus 1/2 T. Think about it. If you look at this game matrix, if I play H, because player 2 is just flipping, I'm either going to get a 1 with probability 1/2 or minus 1 probability 1/2. 0 expected payoff. If I play T similarly, and if I play any convex combination of those two, any distribution over those, I'm just going to get the combination of zeros. So in some sense, I'm player 1, it doesn't matter what I do, but it turns out that I do want to play this mix, because if I play H and player 2 somehow got wind of that, right, and he might deviate from his 1/2 H plus 1/2 T and play T, so he collects the pennies. Okay, anyway, that's just an example of mixed strategies at work. All right. Now I want to give you a little bit more game theory notation. Game theory shorthand. The absence of that clock, or the horizontality of it, makes it hard to see from a distance. I'm psyched that my voice has lasted this long today. It's really kind of cool. Okay, so here's some game theory notation. Shorthand. Okay, this is very typical stuff. You say I'm given an n-player game. And a player, I'm going to an action profile. Given an n-player game and an action profile. A1 through AN for the players. Use this notation, U sub I of AI, comma, A sub minus I, to denote U sub I of A1 through A sub N, where this is meant to be read as follows. Quote, the payoff to player I, given that he plays AI, and the non-I players, the players other than I, play according to A sub minus I, which is shorthand for all the things in A1 through AN that aren't AI. Okay? So that's just game theory shorthand. And that extends to strategies, pure and mixed. You can extend that. As follows. You have things like U sub I of AI against, say, S minus I. That's payoff to player I. when he takes action AI and others, the non-I players, play according to pure strategy profile. Sub minus I for them. So this is going to be like a list of n minus 1 pure strategies. And U sub I of, say, S or sigma sub I, comma, sigma sub minus I. Payoff to player I when he plays sigma sub I, and non-I players play play according to mixed strategy profile sigma sub minus I for them. Okay, and you'll see why this notation is useful as we go along, Max.
So does this minus I mean that it's just some different strategy than AI?
No, it means this is a, think of it this way. This sigma sub minus I is just shorthand for a strategy profile for the players other than I.
Okay. Are they
So-
all the same or just not?
Well, if there's 17 players, say, in the game, there's 16 players other than player I. Say player I is player 11, right? Then sigma sub minus 11 is going to be a list of 15 strategies, one for player 1 through player 10, and one's for player 12 through player 16. And it's just collapsing in that notation. So and often we'll say things like, and this, by the way, expected payoff in both cases. This one isn't necessarily expected, but this one is expected because you have mixed ones going on. But the point here is we're often going to want to say things like, okay, if I'm player 1, what's my playoff for playing C against that? And so on. Against that set of strategies by the opposition. Okay, so that's just notation. All right. Now this brings us to probably the most important concept in all of game theory, and that's the idea of a Nash equilibrium. And it's too late to start that today, so let's leave that for next time.